Hello and welcome to Ms. Barlove's screencast of the properties of water and salinity. Today we're going to be looking into what makes water so special and talking about how saline the ocean is and breaking down that salinity into some more comprehensible terms. Since it is a screencast, please go ahead and put your headphones on now, please. And if you don't have any, just keep the volume down as to not distract any other students working. Here are the learning goals for today. Please push pause so you have time to write them down. Reminder, this is the week 2 learning goals, so you should be on a separate piece of paper. They're going to be page 13 in your binder, and you should have already turned in the week 1 learning goals. If you didn't, please go ahead and put them in your class periods inbox. So what is water? Water is essential to all life. We need it for almost every function. All right, if you guys remember from the screencast yesterday, water makes up 90 to 95% of all plant cells and 70 to 75% of animal cells. So it's really important to all cell functions, not only just the bigger, digestion or breathing. It's even important at the cellular level. So it's important to keep that in mind. The picture on the right is a water molecule. We'll see the 2 hydrogens for the H2 and the 1 oxygen. The rings around these atoms are our electron orbitals, all right? So if you remember from yesterday, electron orbitals, this is where our electrons go. They have specific spaces, and water is a covalent molecule because we are sharing electrons, not transferring them, all right? Sharing, not transferring, okay? So you'll notice here and here, we have 2 electrons being shared, which is a single bond, right? So we have single bonds here, single bonds here. Now, these plus signs are going to become important later on in the screencast. So for right now, don't worry about it. And also right here, it's kind of hard to see, but that's a negative, all right? But this is water in a nutshell. And so we're going to be looking at its 5 specific properties that make it so unique. The first one is that water is a polar molecule. Now, this is a chemistry term you might recall from your previous chemistry class, but if you don't, polar just means that the compound or molecule has both positive and negative ends. So if you recall from that previous picture, I now have one up here. We have a negative side on the oxygen and a positive side on the hydrogen. And what that basically means is that oxygen is taking the electrons more often than the hydrogen is. All right, it's kind of like unequal sharing. Say, for instance, you have a younger brother or sibling and you tell your mom or dad that you're going to share the GameCube or the Xbox equally and you take more time than your younger brother or sibling. That's kind of what that means. All right, so just a quick refresher also, a molecule is just a group of atoms that are bonded together. Now, in addition to the polarity, it's important to note that these bonds in between the oxygen and the hydrogens are called hydrogen bonds. So these bonds right in here, the H and the O, these guys connecting them, are called hydrogen bonds. And we're going to see in a second here why those are so important. So why is it so important that water is polar? Why do we care? Well, these hydrogen bonds are super strong. This lets water be able to bond to itself really, really well, as well as to other polar molecules. If you recall, like attracts like, or positive or opposites attract, and polar attracts polar. So we allow water to bond to a lot of different things. You'll see in the future slides that water is a very sticky substance, and we'll go in further what that means. This allows substances to dissolve in the ocean. This is how we're able to have a salty ocean or a saline environment. Also, it is important to note that because of this polarity and these hydrogen bonds, water is the only substance to exist in all 3 states naturally. Now, what are states? All right, states are the solid, liquid, and gas form. And you've probably experienced all 3 of these forms. Solid water is ice. Liquid water is the water we drink, and gaseous water is water vapor. So if you've ever boiled tea and seen steam from it, that is water vapor. There's also just water vapor in the environment naturally. This feature also will just relate to every other property we're about to talk about. So it's important to keep in mind, again, big takeaway, water is polar and water has 2 hydrogen bonds. Next is water's and ice's densities. Okay, now density, in case you've forgotten, you've probably learned this in a chemistry class and maybe a math class before, but density is just how tightly packed something is. All right, it's how much mass you have in a given space, or mass over volume. Okay, now generally speaking, a solid is more dense than a liquid. So if you've ever seen, if you put a rock inside of, drop it in water, it sinks. If you were to put solid arsenic inside of liquid arsenic, it would sink, right? More dense things sink. In the case of water, however, that's not the case. Look at the picture at the right here. Ice floats. Anytime you've had ice inside of water at a restaurant or at home, all right, that's abnormal. That's not the case with every other molecule or compound or element. And so this is very important. We're going to take a look at this YouTube video real quickly to show that point.
Water is the liquid of life. We drink it, we bathe in it, we farm, cook, and clean with it. It's the most abundant molecule in our bodies. In fact, every life form we know of would die without it. But most importantly, without water, we wouldn't have iced tea. Iced tea. Why do these ice cubes float? If these were cubes of solid argon in a cup of liquid argon, they would sink. And the same goes for most other substances. But solid water, aka ice, is somehow less dense than liquid water. How's that possible? You already know that every water molecule is made up of 2 hydrogen atoms bonded to 1 oxygen atom. Let's look at a few of the molecules in a drop of water, and let's say the temperature is 25 degrees Celsius. The molecules are bending, stretching, spinning, and moving through space. Now, let's lower the temperature, which will reduce the amount of kinetic energy each of these molecules has. So they'll bend, stretch, spin, and move less. And that means that on average, they'll take up less space. Now you'd think that as the liquid water starts to freeze, the molecules would just pack together more and more closely. But that's not what happens. Water has a special kind of interaction between molecules that most other substances don't have, and it's called a hydrogen bond. Now remember that in a covalent bond, 2 electrons are shared, usually unequally, between atoms. In a hydrogen bond, a hydrogen atom is shared, also unequally, between atoms. 1 hydrogen bond looks like this. 2 look like this.
Sorry for that minor hiccup. A janitor just walked through. We'll proceed.
9, 10, 11, 12. I could go on. In a single drop of water, hydrogen bonds form extended networks between hundreds, thousands, millions, billions, trillions of molecules, and these bonds are constantly breaking and reforming. Now back to our water as it cools down. Above 4 degrees Celsius, the kinetic energy of the water molecules keeps their interactions with each other short. Hydrogen bonds form and break like high school relationships, that is to say, quickly. But below 4 degrees, the kinetic energy of the water molecules starts to fall below the energy of the hydrogen bonds. So hydrogen bonds form much more frequently than they break, and beautiful structures start to emerge from the chaos. This is what solid water, ice, looks like on the molecular level. Notice that the ordered hexagonal structure is less dense than the disordered structure of liquid water. And you know that if an object is less dense than the fluid it's in, it will float. So, ice floats on water. So what? Well, let's consider a world without floating ice. The coldest part of the ocean would be the pitch-black ocean floor, once frozen, always frozen. Forget lobster rolls, since crustaceans would lose their habitats, or sushi, since kelp forests wouldn't grow. What would Canadian kids do in winter without pond hockey or ice fishing? And forget James Cameron's Oscar, because the Titanic totally would have made it. Say goodbye to the white polar ice caps reflecting sunlight that would otherwise bake the planet. In fact, forget the oceans as we know them, which at over 70% of the Earth's surface area regulate the atmosphere of the whole planet. But worst of all, there would be no iced tea. Iced tea.
All right. I feel like that video does a pretty good job of explaining why we care that ice floats. But, just to reiterate, because of these hydrogen bonds and the unique polarity of water, we're able to get this crystallized structure. Okay, so the crystalline structure is what allows this to be less dense, or allows the ice to be less dense. And because ice floats, we can still have whole ecosystems exist during the winter or cold months, right? What would happen if the whole ocean froze over? We wouldn't have our marine ecosystems or our freshwater ecosystems. They are allowed to exist during really cold times, which allows for these cute little penguins to still exist all the time. What would we do without penguins? I don't even know. Moving on to the next property. Water takes a lot of energy in order to change its temperature. Now, that's a very vague way of saying these two specific terms, all right? Water has a high specific heat capacity and a high heat of vaporization. Now, these are just two chemistry terms, and they basically mean water needs a lot of energy to increase its temperature or decrease its temperature. You're not going to be responsible for knowing these terms. However, I did include them in case you recognize them from a previous chemistry class. But bottom line, it takes a lot of energy to change the temperature of water. This is how we are able to take super, super hot pennies or any form of a metal and put it in water, and the water doesn't start to boil, right? I'm not sure if you guys have any experience doing that. However, say for instance, you've put a hot plate under some water to cool it down and start washing it. The water doesn't boil. So why do we care? Again, these hydrogen bonds are hard to break. That's why it's hard to change the water's temperature. It's hard to break that bond. So water's temperature is pretty consistent, which helps distribute heat on the earth. That's its job. This also is important in thinking about some global warming implications, right? Our sea level temperature has increased dramatically, which has given rise to recent hurricanes, which has given rise to coral bleaching. A lot of things are not normal per se to certain times of the year and certain regions. That means we have done a pretty good job of changing water's temperature. That involves a lot of energy. Just a food for thought tip there. Now I include Titanic in this picture because this explains why Rose lived and Jack died. If you didn't know, during Titanic and the sinking, the water was the same temperature as the air. It was both relatively close to freezing. All right. Now, if the air and the water are the same temperature, why would Jack freeze and Rose not? Now, that doesn't make much sense. However, since Rose and Jack both have body heat, right, as we do, we all run about 98.6 degrees, all right, the air's temperature changed a little bit more with all the bodies outside of the air. It has a lower specific heat. The water's specific heat is so high with all the bodies in it, it didn't change temperature. That's why Jack froze and Rose didn't. So, again, the theory about the door, if there was room, Jack would have lived. The next property we're going to talk about is cohesion. However, due to the amount of time I have on any given screencast, I'm going to have to push pause here. So you guys are going to have to tune in to the next screencast. This will be Properties of Water and Salinity Round 2.